So in this question, this is a classical frictional friction loss problem. So we have P1, it's given, it's 100 psi, and note that it's after the pump. So we're measuring the pressure at the output of the pump. So the pump power, it's if you're going to take Bernoulli equation, it's not going to be included in my equation because P1 is here. If I'm going to be using this value, P1, which I should because that's what's given for us, and I can't use anything before the pump because I don't have the information for the pump. We need to solve for P2. And again, P2 is right here. So it's before, it's the point supplying the piston, it's not after. The pipe is 45 feet. It's 10 and 5 and 10 and 20. So that's 45 feet. And it has an inner diameter. So D, it's 1.5 inch. The upstream pipe, oh, that's D1. Okay, we have two diameters. The upstream pipe, it's 1.5 inch. That's before the globe valve and it's wide open. I believe they should give us, yeah, the K value is just right there. And the diameter downstream after the globe valve, that's 1 inch. Okay, so this problem will be reviewing the frictional loss in pipes, how to calculate that, and fittings, and then find the total head loss and how to use the Bernoulli equation. And that's how we will be finding P2. Why? Because what I have, if I consider that's the first point, then if we put down the energy equation, which is the Bernoulli equation, it's P1 divided by the specific weight of the fluid. It has a specific gravity, 0.9, plus V1 squared divided by 2G plus Z1. Let's read. Yes, it's all in a horizontal plane, which means it's not vertical. As you can see, it's actually kind of, you're looking, so it's in the same plane and you're looking from the top. So we don't have any difference between Z1 and Z2. Okay. I hope this is clear. We have also the flow rate. It's 30 GPM. So Z1 minus the head loss. That's all what I have because I don't have, again, the head of the pump. It's not included between 0.1 and 0.2. So that's equal to, because I can't just say head of the pump is 0. We do have a pump, but it's not included in my Bernoulli equation. So P2 over the specific weight plus Z2 plus V2 square over 2G. So Z1 and Z2, I'm going to cross these. I have P1. I need to solve for P2. So P2 over gamma is P1 over gamma plus V1 square. I'll bring V2 to the other side and combine them together minus the head loss for the whole system. I have P1. I should be able to find V1, and we will need to do that, the first step. But the main problem here, or the main test, is to find that head loss, which is coming from friction and the elbows that you see there. The 90-degree elbows, we have the K value, it's given 0.75. They did kind of made it simpler for us, so we don't have to dig through how to find the friction loss, but I'll make a note to that. We will need to find the Reynolds number. But either way, I will need to find the velocity in the pipes. After that, I will find the Reynolds number and then the friction loss coefficient. To make it simpler, because we have two diameters, that's why I'm giving you this friction loss coefficient, because you will need to do it twice. One for the pipe that has a diameter 1.5, and one time for the other one. So this could be actually written as P1 over gamma plus V1 square minus V2, the velocities over 2G minus head loss in system 1, that's upstream, and then head loss in system 2. Okay, so that's for the 1.5 inch and that corresponds to the 1 inch. That's actually, it makes more sense because the elbows, those two 90-degree elbows, they are actually in the 1.5 inch, so they have to be here. And this one would take the globe valve because it has a smaller diameter. Smaller diameter has higher velocity, which means more losses. And that's why we need to include that. We did discuss that, but if you can see it, uh, so the head loss in valves or in fittings in general, it's the K value times V square over 2G. Now, those two elbows are already in before and after the elbow, it's 1.5 inch, so it has to be in the first one. Now, the globe valve, it's in between the 1.5 inch and the 1 inch. So, should I say which velocity should I use? Should I use V1 or V2? Usually, we use the higher velocity because it gives me more losses, and I'm trying to find usually the maximum. If I have a pump, I need to know the maximum head of the pump, or I would assume the maximum loss here in order to find P2. I wouldn't take less than that, and that's why we use the higher velocity. The higher velocity is coming from the change in the diameter, so I would use the 1 inch side because it's the area is less. That means the velocity is higher because the flow rate is fixed. All right, let's find V2 first, or V1, it doesn't matter. It's Q over A, in this case A2. Q is 30 gallons per minute. I will multiply that by 3.85. That's the cubic inch per second per gallons per minute. And then the area for 2, it's pi over 4. Actually, we will need those to be in cubic feet per second. So I'm going to multiply that by 0.00223 cubic feet per second. Again, we got this from so 1 gallon is 231, and then if you divide cubic inch, 1 gallon per minute is 231 over 12 cubic feet. And if you want it to be in cubic feet per second, so it would be 231 over 12 cubed times 60. So this should be what we have there. It's 0.002288 and some change. So 231 divided by 12 cubed over 60, 0.002228. So I just rounded that to 223. Divide by pi over 4. The diameter is 1, and I'm gonna put it in foot square. So my velocity would be in feet per second. This one is 12.2 feet per second. We will do the same for the first section. So V1 is Q1 over A1. So we'll only plug here the 1.5 diameter, and I will get the velocity. It's 5.45. And as expected, V1 is less because the diameter is larger, so it should give me smaller velocity. Now, before we dig into the head loss 1 and 2, if we don't have the frictional loss given, then I will need to find the Reynolds number. And then from Reynolds number, I can calculate the frictional loss coefficient, which they gave you the 0.02. Again, because I have two diameters, so I'm going to have two velocities, and then I will have two Reynolds numbers. Remember Reynolds number, or NR, it's V times D divided by the kinematic viscosity. And then we would go to Moody's chart or use Blassi's equation, or if it's laminar, we have that directly. And then from the Reynolds number, I can find F, but I'll have to do that twice. Now, the head loss in general, it's the frictional head loss plus the fittings head loss. For each section, head loss 1, that's F L1 divided by D1 times V1 squared. And that's why I said the first step is usual to find V1, to find F, and then we're going to need it here. Plus, I have two 90-degree elbows times V1 over 2G. Okay, so this is 0.02, the length 10, 5, 10, 25, divided by D1, 1.5 over 12, so they're both in feet, plus 2, what was K, 0.75, and then both are multiplied by V squared divided by 2G. We're doing English units. Okay. And then similarly, head loss 2 would be 0.02. L2 is 20, 1 over 12, that's in feet. Plus, I have now the globe valve. We said that's 10. My velocity this time it's 12.2. Okay, if I can get that, I'll plug these values and I should find my final answer. So this one is 2.54 feet, and here 34.21 feet. Therefore, the head loss is head loss 1 plus head loss 2, or we can plug it directly into my equation. 36.7 feet. Therefore, P2 over gamma is what's P1? 100 psi, 100 pound per inch squared divided by gamma as 62.4 pound per cubic feet times the specific gravity 0.9. So I'll need to convert one of them since I have this in feet. So I'll need to convert this to be in pound per inch squared. So I will multiply that by 144 inch square per foot square. So this with that, and then pound with pound, and then I would have 1 over foot square divided by 1 over foot cube. That would give me feet plus V1 is 5.45 square minus 12.2. That's the two velocities divided by 2 times 32.2 minus the head loss that we just calculated. After we find the answer, we will multiply it one more time by gamma, and we will solve for P2.